10,000 light-years away, there's a dead star spinning fast enough to twist empty space itself, and it might just prove that nothing is actually something. For nearly 90 years, one of the strangest predictions in all of physics has been sitting untested, waiting for scientists to find a place extreme enough to check if it's real. That place turned out to be a magnetar, and what astronomers just found could rewrite what we think we know about the vacuum of space. Let's back up. In 1936, physicist Werner Heisenberg, yes, the same Heisenberg behind the uncertainty principle, made a bizarre claim. He said that even a perfect vacuum, a region with absolutely nothing in it, isn't really empty. According to quantum theory, empty space is constantly buzzing with what are called virtual particles, pairs of particles and antiparticles that pop into existence for a fraction of a second and then vanish again. It sounds like science fiction, but it's a core prediction of quantum electrodynamics, the physics that governs how light and matter interact. Heisenberg's theory said that if you put this empty space inside a powerful enough magnetic field, those virtual particles would behave like a filter, bending and polarizing light that passes through, a phenomenon now called vacuum birefringence. Think of it like light passing through a crystal or a pair of polarized sunglasses, except the crystal here is empty space itself, and the only thing making it act that way is a magnetic field strong enough to align invisible quantum particles. The problem? No lab on Earth has ever built a magnet powerful enough to test it. According to astronomer Dr. Marcus Lower of Swinburne University of Technology, detecting vacuum birefringence requires a magnetic field over 100 million times stronger than anything humans have ever produced. That number alone tells you why this prediction sat unconfirmed for nearly a century, until scientists realized they didn't need to build that magnet. The universe had already built one. Enter magnetars, the most magnetically extreme objects known to exist. A magnetar is a type of neutron star, the collapsed core left behind after a massive star explodes in a supernova. Imagine squeezing more mass than our entire sun into a sphere roughly the size of a city, spinning rapidly and wrapped in a magnetic field over 1 trillion times stronger than Earth's. That's a magnetar. There are only about 30 known magnetars in our entire galaxy, making them some of the rarest objects astronomers can study. The magnetar at the center of this story is called 1E 1547.0-5408, sitting more than 10,000 light-years from Earth. It spins once every 2.1 seconds, and by sheer cosmic luck, its magnetic axis lines up almost perfectly with its rotation axis, which means Earth happens to be staring almost straight down one of its magnetic poles. That rare alignment turned this particular dead star into what researchers are calling the perfect natural laboratory to finally test Heisenberg's 90-year-old idea. To study it, an international team combined data from 3 major facilities. NASA's Imaging X-ray Polarimetry Explorer, known as IXPE, tracked how the X-rays leaving the magnetar were polarized. NASA's NICER telescope, mounted on the International Space Station, added more X-ray observations. And on the ground, the CSIRO's Murayang radio telescope at Parkes, Australia, the same dish famous for receiving the first television images of the Apollo 11 moonwalk, captured the magnetar's radio emissions. Between March and April of 2025, the team gathered more than 140 hours of data, marking the first time scientists had ever recorded simultaneous radio and X-ray polarization measurements from a magnetar. All of that radio data was then processed using Swinburne's Ngargu-Tindabeek supercomputer before being compared against the X-ray results. So what did they actually find? Ordinary telescopes measure how bright an object is. IXPE measures something different: the orientation of the light waves themselves, known as polarization. And what it detected around this magnetar was striking. The X-rays leaving the star showed polarization levels reaching as high as 80% in certain energy bands, nearly 3 times higher than standard surface emission models say should be possible. On top of that, the direction of that X-ray polarization closely matched the magnetar's magnetic field, and it shifted in sync with the radio wave polarization as the star rotated. In other words, 2 completely different types of light, measured by 2 completely different instruments, we're telling the same story, a story that lines up with what vacuum birefringence would predict. The findings were published on August 5, 2026, in the journal Nature, led by researcher Rachel E. Stewart along with a team including Dr. Marcus Lower and several other astrophysicists from institutions across the world. It's being described as the strongest observational evidence yet for vacuum birefringence, a potential answer to a 90-year-old quantum cold case. But here's where it gets interesting, and where good science requires us to slow down. This isn't a slam-dunk, case-closed discovery just yet. Confirming vacuum birefringence with full scientific certainty would require either a sharper, higher confidence signal at a very specific energy level called the vacuum resonance, more magnetars showing the exact same pattern, or a laboratory experiment on Earth that independently backs up what's being seen in space. None of those three things has happened yet. There's also genuine, healthy debate within the astrophysics community. A separate independent analysis, published in April 2026, looked at the same IXP data using a different geometric model and concluded the results couldn't yet be called compelling evidence for vacuum birefringence. In other words, some scientists think this is the real deal. Others say the jury is still out. That tension is exactly how real science is supposed to work. Still, even with that uncertainty, the implications here are enormous. If vacuum birefringence is confirmed, it means we've directly observed quantum electrodynamics operating at a scale and intensity that's completely impossible to recreate anywhere on Earth. It would mean that empty space isn't a passive, inert background. It's an active medium that can bend and filter light under the right conditions. It would close a 90-year gap between theoretical prediction and physical proof, joining a short list of quantum effects, like the Higgs boson, that took decades to move from math on a chalkboard to confirmed reality. And it opens the door to using magnetars as natural physics laboratories for testing the limits of quantum theory in conditions no human technology could ever replicate. Dr. Lower and his team aren't stopping here. They plan to gather more data, refine their computer simulations, and study additional magnetars to see if the same signature shows up again. As Dr. Lower put it, with more data and better simulations on hand, they may finally be able to complete the quest that Heisenberg started nearly 90 years ago. So think about that for a second. A star that died in a supernova, sitting 10,000 light-years away, spinning twice a second, might be the key to proving that the empty space all around you, the space between you and your screen right now, isn't actually empty at all. What do you think? Is nothing really nothing? Or is space itself hiding something we've never been able to see? Drop your thoughts in the comments and follow this page for more real, research-backed space and physics discoveries.